So everyone, we're back here again doing another example. So this is example 3.8. So let's see what it says. It wants to determine the magnitude and location of the resultant of the parallel force system. Woo! Parallel force system is just saying that all of our forces in the end are going to be parallel. They're the same direction. Now the force acts on this horizontal beam AB. All forces are vertical, and it says neglect the weight of the beam. Now how do we do this? Well, first off, we have to find the magnitude of this distributed load. And what is that magnitude? Well, it's going to be the area. It's always the area of our load here. So area of a triangle is 1/2 base times height. The height would be 25 newtons per meter. The base would be 4.5 meters. And that comes out to be 56.3 newtons. Now, perhaps you're wondering, well, why is it applied at 1.5 meters? With rectangles, it's always at the center. Why is it a third for this case? That you find in your textbook. If you look in your textbook, you will find a little graph. It'll show a picture, and it'll tell you that the centroid is at h/3. So we consider this to be the base, this is the point, and so this is a third of the distance. Okay, it's always a third from the big side. A third from the big side. Now, after that, we're going to jump ahead about here. I have to calculate the total resultant force. Now, I do know that I made a mistake here with my little sign. This should have been negative right here. But we have a 56.3 Newton load and a 50 Newton load, both of them acting down, same direction. So our resultant force is going to be 106.3 Newtons. 106.3 Newtons. Now, if you remember, our final equation is going to be sum of the moments is equal to resultant times x bar, which means we got to take sum of the moments. And we can pick any point we want. I typically go with the one on the left just because that's what I'm used to. So let's do that. So it's force times distance, so negative 56.3 times 1.5 minus 50 times 5.5. That gives me negative 359 Newton meters. As a note, it's not negative because the forces are negative. It's negative because each of these are clockwise, and typically I determine that counterclockwise is positive. So you could have made these both positive. You just have to be very careful when you're doing everything else. Actually, don't do that. Just make sure that clockwise is negative. You'll be fine. If you get a number and it says it's off here in the distance, that means that you have the sign wrong, and just switch the sign and make it positive. Your x bar should always be positive. So now with that, we can use that equation I wrote earlier to calculate the position of our resultant force, because it has to have the same total force and it has to have the same moment. So since we know what the moment is and we know what the force is, that leaves us only one unknown with one equation we can solve. And it comes out to be 3.38 meters. And that makes sense. That makes sense. If you have something that's like at either extreme, like right here or right here, you might have made a mistake. You should probably look into that. But that's it for this problem. The big things are, one, check your textbook right here, okay? Check your textbook for the centroid. That's going to be the easiest way to calculate what the centroid is of various different shapes. Two, be very careful with your sign. Up is positive, right is positive, and counterclockwise is positive. That's typically the best way to go about it. And then make sure that your answer makes sense. If it's off the side, that doesn't make sense. Make sure that it's on top of the beam. So, thanks for listening. And I'll see you all next time. Bye-bye.